Okay. Hello and welcome back to Calculus 1, section 3.7, the chain rule. As I mentioned before, chain rule is going to be one of the most used derivative taking techniques, and it will also give rise to one of the most important and most frequently used integration techniques, which we are going to study eventually in chapter 5. So chain rule, let's actually write that right away. So chain rule is the way to take the derivative of function composition. So chain rule is used to take the derivative of function composition. Now, we are eventually going to look into the formula and so on, but let me just give you some motivation here. Let's say you want to take the derivative of x plus 3 squared. Right? Obviously, you would FOIL this, right? Which would give you x, wow, forgot to write the derivative. That's minus 1 right there. There we go. So x squared plus 6x plus 9. And now to take the derivative, you get 2x plus 6. So that wasn't that hard, right? It's a standard problem. You should all know how to do this by now because this is technically 3.3. But hell breaks loose if we take x plus 3 and raise that to the 76th power. Good luck foiling. I'll wait. No takers? I see. Okay. So in this case, we have to figure out a better way to deal with this. Because no, I'm not going to sit and FOIL 76 power, right? So what could I do? Well, you know, the initial thought should be, you know, if all of this over here was just one thing, then I would be able to take the derivative of it. So in my mind's eye, I'm going to make that thing one thing, and then say, well, this is 76 times, and then power of 75. And this is where the blue goes, right? Now we can reveal what that is and fill in x plus 3 in here. And then we are going to multiply by the derivative of that inside. What we just did is we created the chain rule procedure. This part over here is called the chain, that extra derivative step that you go. So now let's write the formula for this and then just start working on 5,000 examples, including the tangent line problem. So we are going to start here with first writing that the derivative of f of g of x is the derivative of the outer function f with g plugged in times the derivative of the inner function, which is g. So this is your chain rule formula. Now, we see over here function composition. And we see over here also function composition. So, as you are looking at this formula, you see that you have function composition play the key role. And if you do not understand function composition, you are doomed, because you can't do any of the problems. So what is this function composition from your pre-calculus thing? First of all, f composed with g, right, that was the initial notation, was you take f and you plug g inside. You need to be masters of decomposing function composition, not just what you, not creating it, right? Because creating, you just use the formula, and it's very simple. So what you do is you say, I'm going to have two functions, say f of x is equal to sine x, and g of x is equal to, let's say, 3x squared. You can create f of g of x by taking the outer function, which is f, that's going to be sine, and instead of its x, you will put 3x squared. But you can also create g of f of x by writing 3, and instead of x, you will have sine x, and then that squared. Better way to write this is 3 sine squared x. Right, that's the equivalent. Now, you are supposed to know how to go from here there in order to be successful with chain rule, because you are asked to find the derivative of sine 3x squared. That's your job. And in order to find the derivative of that, you have to be able to, either mentally or on paper, to decompose into those f and g so that you can fill in the formula that you see up there. Now, that sounds like a lot of mess, but the way I see it is, you know, it's very steps. It's very structured. There we go. So let's see if I can find the derivative of, let's say, e to the sine x, right? E to the sine x. The way I would approach this is, first, okay, I'm recognizing two functions there. I'm recognizing function e to the x. I'm recognizing function sine x. So individually, I know both functions. I'm familiar with them. So that's my step one. Step two is I want to know which one is the main function, which one is the outer function, and then which one is the inner function, because the inner function is that g function that will have its own derivative at the end. So it's important, and it's not arbitrary, obviously, right? So we have to know that. So I want to decompose this in my head. So what's the outer, what's the inner function? What do you think? What's the main function and what's the one that it's plugged in? Yes.
So g is sine x.
Yes. And f is e to the x. Very good. So now you see that if you replace x of f with g, you will get the function we have. Great. So now, if I am trying to take the derivative of this, well, I need to take the derivative of f, and the derivative of f is itself, but I still have to have g plugged in. You see how that works? You find the derivative of f, right, because f prime, you find the derivative of f, and then you keep g plugged in. Well, derivative e to the x is e to the x, but I have to have g plugged in. So that's just going to go back to e to the sine x. And then times g prime. And g prime, well, the derivative of sine is cosine x. And that's the answer. as I said, 5,000 examples. So if you didn't get this one, not a big deal. You will get it next time or the following time. Eventually you will. I mean, you must. You have no choice. This one. So let's start with derivative of something that is going to be good. Square root of x cubed minus x. Square root of x cubed minus x. Again, I'm going to ask for f and a g. What do you think f would be? F? Very good. Square root of x. Nice. And how about g? X cubed minus x. Very good. So this is your first order of business. Again, guys, this much is pre-calculus. And you absolutely have to have this skill to be successful in the rest of the course and future calculus courses. So we decomposed this. Now the derivative of this puppy is 1 over 2 root x. I hope you memorize that. And the derivative of this one is 3x squared minus 1. So those are the side derivatives. Do not put equal sign here, because function is not equal to its derivative unless it's e to the x. So I put these squiggly arrows. I shouldn't. I should have put f prime equals and g prime equals, but then I'm just as lazy as you are, maybe even more. So I'm going to now say the derivative of the outer function, the derivative of f, with g plugged in. Well, that's going to be 1 over 2 square root of, and I have to plug in g. So that's going to be x cubed minus x. Times the g prime, which is 3x squared minus 1. You have to put these parentheses because it has two terms. To make this nice, 3x squared minus 1 divided by 2 square root of x cubed minus x. You do not have to rationalize this one. You can leave it, because we don't really know what the x is, right? It might work out to be something that you can actually square root, so there's no reason to rationalize. Right? So if it's not broken, don't fix it. Just leave it there. Square roots are okay in the denominator if you have functions. What's not okay in the denominator is square root of 3. That's definitely irrational, right? So we just remove. So if you have square root of 3, square root of 5, square root of 9, yeah, in the, your answer, don't box it. Rationalize it. But if you have a square root of x in denominator, leave it. Because x could be 4, in which case, why rationalize, right? Square root of 4 is 2, it's fine, right? So these are the things that you need to pay attention to. Next problem. The derivative of sine x cubed. What's happening there? All right, so who can tell me what f is? X cubed, nice. And g is sine x. Nice. That's the hardest part. To see that this sine is actually sine x everything cubed. That's the same notation, I mean different notation for the same thing. So once you know that, the rest of the problem should not be a problem. Good. So what do we have? The derivative of the outer function, which is 3x squared, but I'm not going to put x. I'm going to put g in there, which is sine x, times the derivative of the inside. The derivative of sine is cosine x. So to write this nicely, there are a few options. 3 sine squared x cosine x. And that would be the answer. Let's see if we can get more stuff done. Here's the population model I talked about earlier. So I'm going to come up with a population model. Say I have population in time t is going to be, say, 500 e to the 0.63 t. Find rate of change. So find rate of change of population in time. So your job is to take the derivative of this. Now, yeah, you memorize the formula for this, but I hope you see it's actually the chain rule that is at work. So to find dp dt, the change of population in time, we copy 500 times 0.63 e to the 0.63 t. So now we compute this. Now the way I'm going to compute this is something that you guys are not used to. If you are interested in quick computing, an interesting way to compute other than taking the calculator and doing it, to multiply 500 by 0.63, you are going to take 100 away from 500, right? Those two zeros, and multiply it into this one, so you actually have 5 times 63. So that's the equivalent. And now, instead of multiplying 5 times this, which you could, it's much better if you multiply by 10 and then divide by 2. So, because it's easy to half in our heads. So 10 times 63 is 630, divided by 2 is 315. So dp dt is 315 e 0.63 t. And that is our calculation for now we got the derivative. So now, I don't know, in years or hours or months, whatever it is, whatever kind of organism you are observing for population, right, going from bacteria all the way to people, something, right, you will use those units and for time and use that one. Good. So let's explain now these derivatives that you were asked to memorize before, and now we can finally understand why and how. So the formula asked you to memorize that the derivative of e to the ax is a e to the ax, and you were asked to memorize that. Now also, together with this and explained in a completely same way would be derivative of sine of ax or cosine ax or any of these. So what do I have here? If I'm looking at the derivative of e to the ax, I'm having f as e to the x and g as ax. Right? Now the derivative of the top is e to the x, and the derivative of the one on the bottom is just a, right? Because the derivative of x is 1. So all I need to do is to put this thing together by saying the derivative of e to the x is itself with g plugged in, so e to the ax, and then times a, which is derivative of g prime, which is g prime, so I'm getting a e to the ax. So as a practice, right, we can think of the derivative of, let's say, cosine of 6x. So what do we get? Cosine 6x. Yes?
Will cosine be f and x to the 6?
Yeah, f is cosine, very good. Cosine x, and g is 6x. Good. Yep. So what's the derivative of cosine? Negative sine, and you have to keep g plugged in. So negative sine 6x times 6. So the answer is negative 6 sine 6x. That will be the answer. Bueno? Find the equation of the tangent. I know you all waited for this. Find the equation of the tangent line for function f of x equals, and now we need to put something cute. What should we put? Well, actually, I can probably let's find the problem on the well, if the book would ever load, that's another issue with it. Yeah, whatever, it's gonna take forever. So square root of x squared plus 3 at x equals to 2, whatever. Oh, now you load. Two. So it's x squared plus 3 under the radical, and x equals to 2. That's the point. Find the derivative, find them. right, let's take a look at this. So first order of business is to find the derivative. And we said, in this case, f is equal to square root of x and g is equal to x squared plus 3. So I will take the derivative, get 1 over 2 root x, but instead of x I have to put x squared plus 3. And then times the derivative of the outside, over the inside, sorry, which is 2x. So now the derivative, if you simplify, 2 and 2 will cancel. You get x over square root of x squared plus 3. Slope m is the derivative computed at the point that it's given to us. So we plug in 2 and I get 2 over square root of 7. And we have to rationalize that because root 7 is not cool to stay in denominator. And I have my slope. 2 root 7 over 7. Fine. To find y, we compute original function at 2, which is the square root of 2 squared plus 3, which is square root of 7. So now what do I have? I have slope is 2 root 7 over 7, and the point is 2 comma root 7. Y equal mx plus b. So y is root 7. M is 2 root 7 over 7 times 2 plus b. Now this is b equals root 7 minus 4 root 7 over 7. And the total of that is 3 root 7 over 7. For the tangent line to be y equals 2 root 7 over 7x plus 3 root 7 over 7. So that is our tangent line at 2. X equals 2. The last problem for today is going to be the difference in solution. So you're supposed to split down the middle. So the derivative of sine cubed x versus the derivative of sine x cubed. Right? So solve these two. I mean, they're different. I wouldn't be asking you if they weren't different. And if you don't know what differences are at this stage in the game, well, we have some calculus issues.
to cover all or some of chapter 3?
It's all chapter 3.
Oh, okay. One more.
Welcome back to Calculus 1, section 2.7, part 1, problem next to last. What concerns me is that you're not talking and not checking the answers, or you already did that and you're ready to leave. All right, I see. So the first one has f to be x cubed and g to be sine x. So derivative is 3 sine x squared times the derivative, which is cosine x. And we had this answer before. The next one has f as sine x and g as x cubed. So the derivative of this one is cosine x cubed times 3x squared, or nicely written 3x squared cosine x cubed as the answer. So it matters where the cube is. It's either on sine or it's on x. Tomorrow, part 2. What else do we have to do? We did a tangent line. We did all of the different types of functions. You know what we didn't do? We didn't do the chain rule that is within the product rule. Quotient rule within the chain rule within the quotient rule, with the product rule looming around. Right? So next class, some of the problems will be turn the notebook sideways and run Latescape so you can actually fit everything in one line. So see you tomorrow.